to operating systems. We'll be covering I'll be covering some topics regarding semaphores and synchronization. So we'll look into the slides today regarding semaphore. So if we look into these slides, you can see that synchronization is a tool that provides more sophisticated ways than mutex logs for processes to synchronize activities. And one of those things is we use is a semaphore. And a semaphore S is basically in semaphore, S itself is a integer variable. Semaphores can only access two indivisible atomic operations, right? So one of those functions that we are concerned about is wait and basically a signal, right? So this two is originally called P function and V function, but the definition of a wait operation is that a wait signal basically wait until S is more than 0, right? And somehow, until it doesn't satisfy this condition, it will continue to wait basically, right? And will be in a busy wait signal, right? The definition of a signal operation, on the other hand, basically increments the value of the S, right? It's an integer variable basically. So in this example here, we see that basically all you need to know is that when we wait, S decreases in value. When we signal, S increases in value, right? So when you issue wait, basically you're running in a busy doing something, right? Okay, so counting semaphores. Semaphore itself is an integer value that can range over an unrestricted domain, right? There is also a type of a binary semaphore where it's an integer value that can range between 0 and 1, right? Or can only be 0 or 1, right? It's the same as the case as mutex logs. Now, you can increment a counting semaphore S as a binary semaphore, right, or an integer one, right? With semaphore, we can solve a lot of synchronization problems that we're going to discuss today, right? Okay, so in the critical section problem, we can create a semaphore mutex initialized to basically 1, right? So what we do is that we call the wait and have a semaphore mutex OS, right? And it will remain in the critical section until it receives a signal to basically allow it to get out, right? Consider in this case we have two processes, P1 and P2, right? With two statements, S1 and S2. And the requirement is that S1 needs to happen before S2. So in this case, we can create a semaphore sync that is initialized to 0, right? So consider this. If we look at this code here, now P1 P1 basically has S1 and then it signals a synchronization, and P2 has a wait and signal and execute S2, right? So in this kind of code, we can see that if any of them executes, right, P2 will have to wait, right, until it receives a signal sync from P1 basically, and that's pretty much how it works. So in semaphore implementation, it must guarantee that no two processes can execute the wait and signal on the same semaphore at the same time, right? This is to make sure that only one person is in the critical section. Thus, the implementation becomes the critical section problem, where weight and signal code are placed into the critical section, right? So it could now have busy waiting and critical section implementation, right? So, but the implementation code is actually pretty short, and little busy waiting if critical section already occupied. Note that applications may spend a lot of time in the critical section, therefore this is not a good problem, right? Okay, let's look at the remaining uh, semaphore implementation with no busy waiting, right? With each semaphore there is a associated waiting queue. Each entry in a waiting queue has two data items, right? Whether value of the type integer or pointer to the next record in the list, right? There's two operations, basically a block, which is place the process invoking the operation on the appropriate waiting queue, or a wake up that removes it from the waiting queue. So you can imagine like there's a queue and they're all waiting for a semaphore to either get out of the queue or being put in the queue, right? So a waiting queue would look like this, right? So you have a def type struct with the integer value with a struct process of a bunch of lists, which all of this is a type semaphore, right? So the implementation looks like this, where we have a wait and we have the semaphore as a pointer, and we make sure and keep track of the pointer as and put things in the queue, right? So again, we have two basically core functions here, wait or signal, right? Wait basically decreases the s value, and signal basically increases the s value, right? So they will be put in a queue when it's being waited, and they will be put out of the queue when it's the s value basically increases, right? So we'll stop it here and we'll continue in the other few sections that is up to come, right? So I'll see you next, right, in the next slide.